We'll now look at a very simple form of a crypto system called the Cesar cipher. So the setup in all of cryptography is the following. You have, let's say, two people, Alice and Bob, and Alice wants to send Bob a message. But there is an adversary, a third party, let's say the NSA, or if you prefer China or Russia, who can eavesdrop. So they can see all the messages that are going out from Alice's device to Bob's device. Okay? What Alice is going to do is she's going to encrypt her message and then send it to Bob, and Bob is going to decrypt it so that even if NSA sees the encrypted message, they won't be able to decrypt it without knowing the decryption process. So the standard protocol is you have a message, then you create a function, which is an encoder or encryptor, and then from this you get a cipher text. This is the encrypted message. And this is the message that is sent to Bob. And then Bob uses a decoder to get the original message back. Usually the encoders and decoders are slightly more involved in that they usually input a key. So an encoder takes two inputs. It takes the message as the input, but it also takes the key that Alice has. Let's call this key A. And then the output is the cipher. And the decoder takes as input the cipher and a key that Bob has and produces the original message. Okay, so these two functions are almost inverses of each other, but they depend on the keys that Alice and Bob have. So let's look at the total amount of data that's going on in here. You have the encoder function, then you have the key A, then you have the decoder function, and then you have key B, and you need all of these four pieces for the entire system to work properly. If there is an adversary who's spying, then what they'll need from you is the decoder and key B. Unless they have these two things, they won't be able to decrypt the message. Now, I will say that typically this part is usually well known. Typically, it's the key that you shouldn't tell anyone. That's, for example, the password. Like Gmail is not the secret. Everybody knows that people use Gmail. It's the password of Gmail that is the secret. So in the same way, it's the key that is the secret. Okay, so that's again a very broad explanation of how crypto systems work. Now, having said that, we'll start with a system that is almost trivial to break, but we have to start somewhere. So we'll do a Cesar set. And so the encoder for this system is shift right by key A. Oh, for this system, you have key A is equal to key B. Okay, so Alice and Bob share the same key. So this is already a problem in the Cesar cipher. The two parties need to have a common key between them. And this raises a meta question. How are they going to communicate that key? What if there's an eavesdropper while that communication is taking place? So first we need that key A is equal to key B, that both Alice and Bob have the same key. And then the encoder function is simply shift right by key A. And the decoder function is simply shift left by key A. And very simple, let's explain. So I have my alphabet A, B, C, D, E, and so on. Let's say my message is, I don't want to do this too complicated, so I'll just do BAD. I can see those letters here. And let's say my key is 3. Okay, so then what Alice is going to do, or what the encoder is going to do, is it's going to take B and is going to shift right by 3. What do I mean by that? Let's write the letters A, B, C below itself, but then shifted by 3. So A shifted 1 goes here, shifted 1 more goes here, shifted 1 more goes here. So that's where A will start, B, C, D, E, F, G, and so on. And then they'll come back and I'll get X, Y, and Z. Oh, sorry, I want to shift B to 3, right? So that's here. And that gives me E. Then A shifted 3 to the right. So this is A, it's shifted 3 to the right, and that is D. And then D shifted 3 to the right is, I need to write one more letter, that is G. And so what Alice will do is Alice will send the message EDG to Bob. And Bob knows that the key is 3. So Bob will simply shift E back by 3 and get B. He will shift D back by 3 and get A, and shift G back by D and get D, and you will get the message bad back. This brings us to model arithmetic. There is a very nice way to encode this using mathematics. So first thing we'll do is now I'll replace letters by numbers. So for example, I can do A is equal to 1, I can do B is equal to 2, C is equal to 3, 4, so on. Okay, then you will convert the message to numbers. So B gets converted to 2, A gets converted to 1, and D gets converted to 4. If you want to be clear about where your numbers start, maybe let's make them all 2 digits. So it's 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, all the way up to 0, 8, 0, 9. And then we get 10, 11, 12, up to 26. So this will then be 0, 2, 0, 1, 0, 4. So that's the message in numbers now. Every two digits are corresponding to 1 letter. Okay, then I'm going to add 3, but I'll do it mod 26. Why mod 26? Because my numbers only go up to 26. So every time I go beyond 26, I just find the remainder mod 26 and like make a cycle back. So then this becomes 5, 4, and 7. Okay, and this is the message that Alice will send to Bob. And then what does Bob do? Bob simply subtracts 3 mod 26. Again, so that like if your number was 1 and you subtract 3, you will get -2. But then you do mod 26, and that is you're finding the remainder that -2 leaves mod 26, that's 24. Okay? So that's why we're doing mod 26, so that it cycles around once you cross 26. And these numbers then will go back to the original number 0, 2, 0, 1, 0, 4. And then Bob can then convert these into B, A, D using the dictionary that he has. So that's how you communicate using the Cesar cipher. It's very simple cipher, not practical, but it explains the basic principles of cryptography.